Have you ever looked up at the night sky and wondered just how vast the universe really is? It's a question that has puzzled humans for centuries. This vast, unfathomable universe of ours. It's so expansive that we've had to invent a whole new unit of measurement just to make sense of it. Enter the concept of light years. It's not a measure of time, but of distance, the distance that light can travel in 1 year. To give you an idea, light can zip around the Earth 7.5 times in a single second. Now imagine it speeding along for an entire year, and you'll start to grasp just how far a light year really is. Astronomers use this colossal scale to gauge the enormous distances between celestial bodies. They're not just measuring space, but time, because the light we see today from distant stars actually started its journey billions of years ago. So, the next time you gaze at the stars, remember, you're looking into the past and across billions of light years. Ever pondered how everything around us came into existence? It all started with a Big Bang. Imagine the universe, all of its galaxies, stars, planets, and everything else that exists, compressed into an infinitesimally small, dense, and hot point. This is what scientists refer to as the singularity, the starting point of the Big Bang. Around 14 billion years ago, this singularity started to expand, and it's been expanding ever since. But let's clarify something here. When we say Big Bang, we don't mean an explosion in the conventional sense. It's not like a bomb going off with fragments flying out into the surrounding space. In fact, the Big Bang was not an explosion in space, but rather an explosion of space. So think of it as the rapid stretching of space itself. As the universe expanded, it cooled down, and the energy present in it started to transform into matter. You know, the stuff that makes up you, me, and everything else around us. Now, you might be wondering, if the universe is still expanding, where's the edge? What's beyond it? The answer is fascinating and mind-boggling. According to the current understanding, the universe has no edge, and it's not expanding into anything. It's just expanding, like a balloon being inflated. This expansion is not slowing down either. It's actually speeding up, thanks to a mysterious force we call dark energy. And what's even more interesting is that we can still detect the remnants of the Big Bang today in the form of cosmic microwave background radiation. This is like the universe's baby picture, showing us its state a mere 380,000 years after the Big Bang. The Big Bang theory, thus, provides a comprehensive explanation for the birth and evolution of the universe. It's a testament to our human curiosity and our relentless pursuit of knowledge about the cosmos. The Big Bang theory gives us a timeline of the universe, dating back nearly 14 billion years. What keeps us grounded and the planets revolving around the sun? The answer is gravity. Imagine a world without gravity. We'd be floating around like untethered balloons, and there wouldn't be any stars or planets, only a cosmic soup of particles. Gravity is the invisible glue that holds the universe together. It's an unseen force that pulls objects towards each other. The more massive the object, the stronger its gravitational pull. Think about an apple falling from a tree. It's not that the apple is particularly fond of the earth, but gravity pulls it down. The same principle applies to everything else in the universe. From the smallest dust particle to the largest galaxy, gravity is at work, relentlessly pulling. Let's take our solar system as an example. The sun, the most massive object in our solar system, exerts a strong gravitational pull that keeps the planets in orbit. Without gravity, the planets would simply drift off into space like wayward children without a guiding hand. But gravity doesn't just keep us grounded or the planets in orbit. It's also responsible for the structure and behavior of the cosmos. It's the architect of the universe. It shapes galaxies, causes stars to form, and even bends light. Yes, gravity is so powerful it can warp the path of light, a phenomenon we call gravitational lensing. Yet despite its omnipresence and might, gravity remains a mystery. We know what it does, but we don't fully understand how it works. Some theories suggest it's a wave, others propose it's a particle, while yet others posit that it's both. Regardless of the exact nature of gravity, its effects are undeniable. So next time you look up at the night sky, remember that it's gravity that's keeping all those twinkling stars and galaxies in their places. It's gravity that's keeping our feet firmly planted on the ground. It's gravity that's making the universe as we know it possible. Gravity, the silent puppeteer, shapes the cosmos and keeps everything in its place. Did you know time can stretch and squeeze depending on where you are and how fast you're moving? Indeed, the concept of time dilation, a peculiar reality of our universe, proposes just that. This mind-bending phenomenon is intricately linked with Einstein's theory of relativity, a cornerstone of our understanding of the cosmos. To simplify, imagine time as a flowing river. Now, this river doesn't always flow at the same speed everywhere. It's affected by the terrain it traverses. The speed of the water slows down when it hits a massive rock, or speeds up when it plunges down a steep slope. Similarly, time also ebbs and flows, influenced by speed and gravity. When we talk about time being influenced by speed, we're referring to what's known as time dilation due to relative velocity. According to Einstein's special theory of relativity, the faster an object moves, the slower its time ticks relative to a stationary observer. This means if you were to embark on a spaceship journey at near light speed and return, you might find that while you've aged only a few years, decades have passed on Earth. On the other hand, time dilation due to gravity, as predicted by Einstein's general theory of relativity, explains how time runs slower near massive objects. Picture a clock at the edge of a black hole. Its seconds would stretch into what might seem like eternity to an observer far away. So, if you were to visit a planet orbiting close to a supermassive star, your wristwatch would tick slower than the clocks back home. These concepts might sound more like science fiction than science fact, but they've been experimentally verified with atomic clocks on airplanes and satellites. So, while time might seem like a constant, unyielding force here on Earth, out there in the cosmos, it's a flexible fabric warped by the dance of matter and energy. So in the realm of space, the ticking of time isn't as straightforward as it seems on Earth. What's invisible, incredibly dense, and sucks everything in, even light? A black hole. Black holes, the cosmic vacuum cleaners, are one of the most enigmatic and intriguing phenomena in the universe. They're objects of such extreme density that their gravitational pull is inescapable. But what exactly are they, and how do they form? The story of a black hole begins with a star. Specifically a star that's several times more massive than our Sun. As the star ages, it burns through its nuclear fuel. When this fuel runs out, the star can no longer support its own weight and begins to collapse under its own gravity. This collapse results in a supernova, a massive explosion that can outshine entire galaxies. What remains after the supernova is a dense core. If this core is massive enough, it continues to collapse until it forms a singularity, a point of infinite density. This singularity, surrounded by what we call an event horizon, is what we know as a black hole. The event horizon is the point of no return. Anything that crosses this boundary, be it matter or light, is sucked in and can never escape. You might be asking, if nothing can escape a black hole, how do we even know they exist? Well, while we can't see black holes directly, we can observe their effects on the surrounding universe. They distort the space around them, causing light to bend and stars to seemingly